Welcome back to photosynthesis. This is part 4 of our discussion, and as what we're going to look at today are the light reactions. And so last time we looked at how pigment molecules can absorb photons of light, and an atom in a pigment becomes excited, and that excitement can ultimately result in the transfer of energy, or the transformation of energy from the light form to a stored chemical potential energy form that is an excited electron. So what we're going to do today is look at how the chloroplast, more specifically proteins in the thylakoid membranes, use the light reactions to harness the energy in that excited electron to synthesize ATP. Now, some of this is going to be familiar to you because we're going to use some electron transport chains just like we did in cellular respiration. So a lot of complexity today. Don't worry if you want to watch this several times, and probably have to do a lot of extra reading and watching of videos that I've posted online for you. So let's get started with this. Okay, here's a piece of art that you don't have in your book. So if you need this, pause the video and take a screenshot of it. So let's orient ourselves to start with here. We talked about pigment molecules last time capturing light energy. Here is such a pigment molecule, and that would be absorbing a photon of light, probably from sunlight, but could be artificial light, and in comes the photon, and the pigment absorbs the photon of light. We have an electron excited, collapses back down to its low energy ground state, and another photon of light is emitted, and that photon of light is absorbed by an adjacent chlorophyll molecule, and so the same thing happens. And so effectively that photon of light kind of ping-pongs around the reaction center, or the light harvesting complex, until that molecule P680, which is that special chlorophyll, gets hit by a photon, and that leads to an electron there getting excited, and rather falling back down, it gets passed directly to the primary electron acceptor, which, remember, is this thing up here. Now, the art's a little bit different, but hopefully you can see that functionally things are the same. So then we've got to replace the electron that's been removed when we have oxidized P680. So we've got to resupply P680 with electrons that it just lost up to the primary electron acceptor. So we've got to replace those electrons, and we do that by oxidizing water, remember, down here in the bottom left. So we oxidize that water, and the electrons come into P680. P680 is now reduced, and that is going to give us oxygen and some protons that we can then use for other processes. So we've now got a high energy electron up here in the primary electron acceptor. So we've got a high energy electron up here. The challenge now becomes to use the rest of the light reactions to convert the chemical potential energy in that excited electron into NADPH, and to produce a molecule called NADPH. And we'll talk about the function of that when we get to the Calvin cycle. So what happens next? So the electron that's up here in the primary electron acceptor gets passed into an electron transport chain, and the reason it does that is because of differences in electronegativities. So this little carrier protein here in the membrane of the thylakoid, this carrier protein is more electronegative than the primary electron acceptor, so the electron gets donated freely from the primary electron acceptor to this protein carrier, and then that protein carrier shuttles the electron into a larger transmembrane channel protein, which is going to move protons across the thylakoid membrane and into the thylakoid space. So this is the lumen of the thylakoid. This is inside, and out here at the top is the stroma. So the protons are going to be pumped through this protein into the space inside the thylakoid. So these protons, and I'm not going to have a very easy job drawing H plus here, sorry, my drawing's bad. That's what happens when you use a mouse. So those protons are going to get pumped. Where's the energy coming from? Now remember, when electrons move to more electronegative carriers through an electron transport chain, each time they move, they give up energy. And so what's happening is we have the oxidation of the primary electron acceptor, the reduction of this carrier, the oxidation of the carrier, the reduction of this protein here, and as that happens, energy is given up and protons are pumped into this space inside the thylakoid lumens. The electrons keep getting passed. They get passed to another carrier protein, and the job of that is to then shuttle those proteins to another photosystem. So far I've only introduced you to one photosystem, and that was called photosystem 2. So that was the first photosystem we talked about. There's a second photosystem that's involved in the light reactions called photosystem 1. So let's talk about photosystem 1 now. So the electrons have moved from over in photosystem 2 through an electron transport chain, and they're delivered to a special chlorophyll called P700. So those electrons in P700 are now low energy. As they came from a high energy in photosystem 1, they moved down the electron transport chain. They've ended up at low energy. Now, low energy electrons aren't going to be much use for us. So what we're going to do is re-energize them, and we're going to re-energize them so we can make this high energy electron carrier, NADPH, and that's needed in the Calvin cycle. So what's going to happen is low energy electrons arrive here in P700, and photons of light are going to excite pigment molecules just like we've had happen in photosystem 2, and we have the electron excited, collapses back down to the ground state, and then another photon is emitted. Same thing happens, excitation, sinking back down to the ground state, a release of a photon. So that photon ping-pongs around the light harvesting complex until it hits the special chlorophyll P700. That causes the low energy electron that just came in from the electron transport chain to be re-energized and donated up to another primary electron acceptor in photosystem 1. So the mechanism of exciting the electrons is the same in photosystem 2 and photosystem 1. The main difference that you've got to pay attention to here is the source of electrons. In photosystem 2, the electrons come in from water. But in photosystem 1, the electrons are coming in as low energy electrons from the electron transport chain, ultimately from photosystem 2. So those high energy electrons, which are now up here in the primary electron acceptor, get passed into a membrane carrier protein, and ultimately they're used to convert a molecule called NADP to a molecule called NADPH. Now, NADPH is somewhat like NADH, which we talked about when we talked about cellular respiration. So NADPH, like NADH, carries high energy electrons. So that's how these photosystems work together. There are 2 points that you've got to take from this. One, the movement of these electrons from photosystem 2 to photosystem 1 through this electron transport chain releases energy, which allows us to pump these protons into the thylakoid lumen. And so that means we've got a high concentration of protons down here, and we're going to use that in a moment to make ATP. The second thing is photosystem 1 is going to re-energize the low energy electrons from photosystem 2 and make this molecule NADPH. So let's look at what this proton gradient is used for that we just built using the electron transport chain. So again, here's another piece of art that's not in your book. So if you want a copy of this, take a screenshot of it and use that for your notes. So what you can do is work out in this diagram what's happening based on what we just talked about. Photosystem 2 over here on the left, electron transport chain in the middle, photosystem 1 over on the right. And you got to bear in mind there are thousands of these working together throughout the thylakoid membrane. And here is our NADPH being made. So let's just look at the electron transport chain. So remember, what we're going to do is we're going to move these protons through these 2 carriers here, these two pumps here, to build up a concentration gradient of protons in the thylakoid lumen. Now, why do that inside the thylakoid lumen? Why not do it in the stroma? Why not pump them in the other direction? It's easy to concentrate things in a small volume, and so that's why we use the thylakoid lumen. It's also why we use the intermembrane space between the outer and inner membranes in the mitochondria, because it's a small volume versus the cytoplasm or the matrix, and so you try and concentrate things in small volumes. And so we make a proton gradient in here, and just like we saw with cellular respiration, ATP synthase is an enzyme which can use a proton gradient to make ATP. So we've created a situation where we've got a high proton concentration inside the thylakoid, low proton concentration outside. So we've got low pH in here, high pH out here. So protons are going to move, if they can, down their gradient from inside the thylakoid lumen into the stroma. And as they do that, they release free energy, and the free energy is used to convert ADP, an organic phosphate, into ATP. So here is really the second main function of the light reactions. It's to make ATP. Now let's not say the function of photosynthesis is to make ATP, because we're going to use that ATP in the Calvin cycle. So let's just look at the art that you have in your book, so that if you're looking at your book, you can relate what you've seen so far. This art in your book is a little bit more complicated. You shouldn't be worrying about all these individual molecules or individual components in photosystems, but what you should be able to do is recognize water being oxidized, light exciting electrons in pigments, and then electrons from water being energized, pass through an electron transport chain, protons being pumped into the thylakoid lumen, electrons re-energized in photosystem 1 and passed to be used to make NADPH, and the proton gradient we generate in the thylakoid lumen is used to make ATP. And so the point of the light reactions is to use electrons from water to create a proton gradient to make ATP, and to use electrons from water which get excited by the photosystems to make NADPH. Those are the functions of the light reactions. Let's take a quick look at the energetics of these electrons. It's really important to understand how the energy of the electrons changes as we look at the electrons moving through the photosystems and the electron transport chain. So you can think about this as a little graph, and so let's put the other axis on here. And this axis along the bottom here is going to be the position in the process. And so at the end we've got NADPH here, and at the start we're going to be looking at electrons in water. So when the electrons come into photosystem 2, they're a relatively low energy state, and they get energized and excited and captured by the primary electron acceptor. Then as they move through the electron transport chain, they lose energy, and remember that energy is used to pump protons into the thylakoid lumen. So we've got low energy electrons arriving over here at photosystem 1. They get re-energized by an input of light, and so they get re-excited. Now they've got a high energy state, and as they pass down finally to NADPH, they've lost a little bit of energy, but they're still really high energy at that point, and we get that high energy electron carrier NADPH. So this is called the Z scheme, because if you look at it, it's like a Z or a Z on its side. I guess you can call it the N scheme as well if you like, but it's called the Z scheme or the Z scheme, and that describes the energetics of the electrons as a function of position in the light reactions. So let's finish up by taking a few questions. I've got 5 questions here, so I will leave these with you, and I will just put the answers in so you can see what the correct answers are. Okay, and here we go. Let's see how you get on with these. Here comes the second question. Here's the third question coming up now. And here comes the fourth question for you. So the last couple of questions there are looking at the relationship between structure and function, and a comparison between those relationships in chloroplasts and mitochondria. And it's really important that you're able to do that kind of comparison. So pay attention to those 2 questions, because you'll see similar questions to those coming up on assignments. And here's the 5th and final question, and then we'll wrap it up. Okay, so what we've talked about in this video is the functions of the light reactions, which is to use light energy to energize low energy electrons from the oxidation of water, and to use those electrons in an electron transport chain to make a proton gradient that's then used to synthesize ATP, to then re-energize the low energy electrons that came from the electron transport chain in photosystem 1, and then pass those to NADP to make NADPH. And the ATP we make here and the NADPH we make here are going to be used in the Calvin cycle, and we'll be looking at it here shortly. So we'll wrap it up there, and I will speak to you soon.